All right. So this is day 2 of rational functions and their graphs. And today we're going to get into the actual sketching of the graphs and talk a little bit more about some of the characteristics of these things. So to start with, we're going to find the domain. Our EQ is how can I sketch a rational function using crucial characteristics. And so the warm-up is going to be the characteristics that we found in section 8.3.1. And that is the domain, the point of discontinuity, and the intercepts. So this should actually be y equals. It's not. So in order to find all that information about this function, I first need to factor it. The bottom is a little bit easier to factor because it's just regular x squared or 1x squared. So for that, if I find factors of -8 that add to +2, that is not -4. So here I did -4 and +2. Those do multiply to -8, but they add to -2. So what I need to do is switch the symbols around here. So it should be x plus 4, x minus 2. And then we also have to factor the top. Some of you have learned different techniques for factoring 2x squared plus 5x minus 12. I'm going to go over here and just factor it the way that I know how. So I'm going to go ahead and multiply a times c. So the front term and the back term. That gives me -24. And then I want factors of -24 that add up to 5. So if we find numbers that work there, I see that 8 times -3 equals -24. And if I add those numbers together, I do get 5. The trick with this is now those are the terms that I need to I need to replace the middle term with. So I keep the 2x squared, I keep the -12, but then I'm going to go ahead and replace the middle with plus 8x and -3x. Now that that's done, I'm going to go ahead and split. And just side note, right, 8x minus 3x is the same as plus 5, so that's why I can do this. Split this in half, and now we just find the GCF of each half of the problem. So here I have 2x times x plus 4. And then on the right side, I can take -3 from both those terms. And if I do, lo and behold, I am left with x plus 4 again. This is essential when you're doing this type of factoring. You need to see the same thing in parentheses there. So that means the top factors into x plus 4 times 2x minus 3. Okay, so that is going to be how I can replace the numerator of our function. So this would be x plus 4 times 2x minus 3. Okay, I'm going to take all this stuff and just kind of shrink it down a little bit. Okay. There's that off to the side. So now I want to know what's the domain of this function, and I see 2 sets of parentheses in the denominator, which means I'm probably going to have 2 numbers that are not in the domain. Here I have x equals -4 and +2. I do see that I can remove that x plus 4 because it is duplicated in both the top and the bottom. So that means I can write this fraction, or write this function a little bit simpler as 2x minus 3 over x minus 2. So that means since I was able to remove the x plus 4, I have a hole in the graph at x equals -4, and the 2, which I could not remove, is a vertical asymptote at x equals 2. Okay, then the last thing I want are the intercepts. So to find the x-intercept, if you recall, that means that the y-coordinate has to be 0. So it's 0 over 2x minus 3 over x minus 2. What we talked about in 8.3.1 is that in order for a fraction to equal 0, the numerator has to equal 0. So I'm essentially trying to figure out what x value makes 0 there. If I go ahead and solve for x, I get x is equal to 3/2 or 1.5. And that's actually not my answer. So that means the x-intercept is 1.5, 0 is where that thing crosses the x-axis. And finally, I have the y-intercept is my last characteristic I'm looking for. And that is, what do I get for y if I plug in 0 for x? So I'm going to write this function as having zeros in place of the variable x. 0 minus 2. What I get here is negative 3 over negative 2, which is 1.5. So that means the y-intercept is 0, comma 1.5. It's not too often that the x and y-intercepts are the same number, but it happens every once in a while. So here I have a whole and a vertical asymptote. So we're going to take a look at this graph real quick, because this is basically what we're doing in this lesson. So I'm going to type in the original function just to Desmos real quick. We will be using the graph. I'll show you how to use the graphing calculator with all this stuff as well. 2x squared plus 5x minus 12 over x squared plus 2x minus 8. So I'm going to put in x equals 2 for my vertical asymptote, just so I can see that there. And then, if I look, I see there's my x-intercept of 1.5, there's my y-intercept of 0, comma 1.5, and then we had a hole right here at negative 4. So there's my undefined piece. So all those characteristics come together to make this interesting. It's actually some similarities to the graphs that we've studied before, but that's, for now, we're just writing it as this list of characteristics. So, okay, last new thing that we need to talk about today are horizontal asymptotes and end behavior. So again, a horizontal asymptote is a line that the graph approaches as it moves out to the outsides of the graph. So the key here is that the horizontal asymptote can only occur as a graph is heading towards infinity. Okay. And the key to this is that this is in the x direction. Okay, meaning right or left. So you can't have an asymptote. You can't have a horizontal asymptote like in the middle of the graph, because it has to continue on forever, either to the right or to the left. So you're looking at the edges of the graph to find your horizontal asymptotes. Your horizontal asymptotes are also called the end behavior of the graph. End behavior basically just means like what line is your graph approaching. So where is it getting close to? Which is just another way of saying horizontal asymptote. The quickest way to find the end behavior or the horizontal asymptote is I am only going to look at the highest degree term on each side of the function. Okay, and highest degree term basically means highest power. Okay, so I'm going to look at just the highest power term, which means I'm going to look at just 2x squared from the top, and I'm going to look at just x squared from the bottom. Okay, and we can talk in class about why I'm only looking at those terms, but I'm essentially going to take this function and ignore all the other stuff, and I'm going to write it as 2x squared over x squared. Okay, again, ignoring the plus 5x and the minus 12, and this is only to figure out what is the end behavior and is there a horizontal asymptote. So if I look at this fraction 2x squared over x squared, I can actually cancel out these x squareds, and this just becomes 2. So what we're going to say for the end behavior is that the technical way to write this is you'd say as x approaches infinity, y goes to 2. Okay. Again, we are always going to use infinity here because we are talking about the far outside regions of the graph, and I could probably also say as x approaches positive or negative infinity. So as I move to the far right, or if I move to the far left, that graph is going to be approaching y equals 2. And that's actually going to be our horizontal asymptote, and we'll get to that in just a second. But to find the end behavior of the graph, we are going to just narrow down the function that we have into one term from the top and one term from the bottom, and then simplify from there. Okay, so we're going to, again, just practice with this end behavior stuff. So if I look at just the highest power, again, I'm not looking at the highest number, like this is 15, that's the biggest coefficient. I'm looking for the biggest power on top and the biggest power on bottom. This then becomes 4x to the fourth over 8x to the fourth, and I want to try and simplify this. Okay, the x to the fourth can cancel out, which gives me 4 over 8, and then 4 over 8 I can reduce to 1/2. So the end behavior of this function is as x goes to infinity, then y is approaching 1/2. Again, we'll look at what all that. We'll take a look at graphically what that means in just a minute. But for now, that's how you study this a lot more in pre-calc and calculus. But for now, we'll just write it like this. Keep it a little bit simpler. The second example, I tried to mess with you a little bit. Again, we are looking for the highest power on each side. And so for this, I have negative 16x squared on top and negative 20x to the third on bottom. Okay. So if I simplify this, I have negative 16x squared over negative 20x to the third. In this case, the powers don't match. So I can cancel out 2 of those x's. But what that does is reduces the x to the third in the bottom. So think of it like this. This is x squared on top. This is x to the third on bottom. So those x's cancel, those x's cancel. And what I'd be left with is negative 16 over negative 20x. The 16 and the 20 can both be divided by 4, negative 4, and I would have 4 over 5x. Okay. So one way you could write this is as x approaches positive or negative infinity, y is approaching 4 over 5x. That's its end behavior. We'll talk about what that actually means for the asymptotes in just a minute. But again, if we're talking strictly end behavior, we can write it just like that for now. And then finally, we have this last one. I have 6x squared on top and 8x on bottom. So if I simplify this function down into just this, and again, I can only do this because I'm looking for the end behavior. Any other time, you can't just like ignore all the other stuff. You have to include what's going on there. Here, one of the x's on top will cancel the x on bottom. So I'd have 6x over 8. The 6 and 8 can be reduced by 2's. So I'd have 3x over 4, which means as x goes to positive or negative infinity, y is going to go towards 3x over 4. Again, right now we're writing out the end behavior, and we're going to talk right now about what that means for whether or not a graph has an asymptote, because some graphs do have horizontal asymptotes, but a lot of graphs don't. So that's end behavior. The general rule is this. This is kind of written out. This is like the book definition. Essentially, if the numerator has the highest power, so when you're looking at the end behavior and you look at just the largest degree or the largest power in top and bottom, if the numerator has the highest power, then there is going to be no horizontal asymptote. Okay. The graph is going to, like, off to the sides, it's going to go up at an angle, or it's going to go down at some sort of angle, but it will not like go flat at the sides. If the highest power in the top and bottom is the same, okay, so if the largest power is the same on both top and bottom, then this will have a horizontal asymptote, and that will be at y equals, and then all I'm doing is taking the coefficients. So this, right now, this seems like, what the heck are you talking about? But we're going to look back at the last 3 examples we just did, because each of those last 3 examples fits one of these 3 categories. And so we'll see what that means, or what it looks like graphically. And then finally, we have if m is less than n, meaning if the bigger power is on the bottom, that will always result to a horizontal asymptote at y equals 0. Okay. One thing to be aware of, like, you don't have note sheets for tests, you don't get note cards, but this information will be provided to you almost exactly as this looks right now. So this information will be given to you on an assessment. So if we take a look at those three, okay, we saw that this simplified down into 1/2, okay, which means, like, if we think about the fact that the x to the fourth and the x to the fourth cancel each other out, that 4/8 reduced to 1/2, which means this thing has a horizontal asymptote at y equals 1/2. Okay. Just to prove that to you real quick, I'm going to type it in. So we got big old fraction, 4x to the fourth. I'm actually not even going to type in the whole fraction. I'm just going to type in the largest powers. That's a lie. I'm going to type the whole thing. Minus 15x squared plus 10. And then this is minus 18x and plus 11. Now, this is a ridiculous looking graph. Okay, there's some craziness going on here. But what our focus is not so much on what's going on in the middle, but what's going on the outside of this graph. Okay, and so if I put on y equals 1/2, you can see that the graph in red, as it moves towards -5, -6, and so on, it is approaching or getting closer to this line, y equals -1, or sorry, y equals 1/2. Okay, and sure enough, on the other end of the graph, okay, there's some craziness in the middle. But if we just focus on the outside, we can see that the red line is approaching the blue line, and it never quite gets there. So that's how you can graphically see the horizontal asymptote, right? And that's what it's going to look like when we do have a graph. So we're going to be kind of putting all the stuff from 8.3.1 together with this, but what you should be looking at is the right and the left ends when you graph these things. All right, there's that one. This one, the fraction that we had was -16x squared over -20x to the third if I took the biggest and smallest power, which gave me 4 over 5x. The rules that we just looked at in the previous slide said that if the bigger power is on the bottom, then you will always have a horizontal asymptote at y equals 0. Okay, and in a nutshell, the reason is, if you pick a very large x value, let's say 1,000 or 1,000,000, and you plug in that x value right there, let's say you had 4 divided by 5,000,000, okay, that is such a small number, 4 divided by 5,000,000, that it is so close to 0 that it's like just above 0. And that's the whole idea behind a horizontal asymptote, right, is that you're getting closer and closer to that number, but never quite reaching it. And so if I made the x value bigger, I would be dividing by a bigger and bigger number, which would get me closer and closer to 0. I'm not going to put that one into the graph. If you want to put this into Desmos just to see how the horizontal asymptote shows up, then go for it. And then this last one, 6x squared, was my largest term over 8x. That reduced to 3x over 4. Because the bigger power was on top, we don't have a horizontal asymptote for this graph. Okay, and I'm just going to throw this one into Desmos just so we can see that there is indeed no horizontal asymptote. Minus 12x plus 10 over 8x minus 9. Okay, we see that there is a vertical asymptote, but you see how the graph to the right here, it's not leveling off. It is kind of slanting and going up at an angle, and the same thing is happening on the left side, that is going down and to the left. That is, if you take pre-calc or calc, this is technically called a slant asymptote. We're not going to cover it. What we need to worry about is that there is not a horizontal asymptote. So these are the three situations. You have a horizontal asymptote at a number, a horizontal asymptote at 0, or not one at all. So what we're going to do is we're going to sketch the graph of this thing using all the stuff that we did in 8.3.1, as well as this idea of horizontal asymptotes. So horizontal asymptotes do kind of like fly up the ranks, and they become the number one overall characteristic that we have to figure out first. So what I'm going to do is I'm going to look at just the biggest terms here. I get x squared over x squared. Those would cancel each other out, and I would just get 1, which means there is going to be a horizontal asymptote here. Horizontal asymptote at y equals 1. Okay. Once I have the horizontal asymptote done, I can get rid of all this stuff, and I can go about what we did in 8.3.1, which is to factor the top and the bottom and kind of do the rest of the problem. So I'm just going to kind of put this over here, and then we'll go about doing the rest of this thing. So next is I'm going to factor this. So I'm going to write it in factored form. So we got y equals x plus 4 times x minus 3. That's how the top factors. And then the bottom is x plus 2 and x minus 2. Okay. So there's a factored version. What's my domain? Well, I know that the domain is x cannot be 2 or negative 2, because I'd be dividing by 0. Neither one of those is removable because I don't have an x plus 2 or an x minus 2 in that denominator. So they are both vertical asymptotes. So I have vertical asymptote at x equals negative 2 and a vertical asymptote at x equals positive 2. And then I want the x and y intercepts. So to find the x and y intercept, I'm going to plug in 0. So for the x-intercept, that's going to plug in 0 for y. And again, by this point, like I don't even need to write the entire fraction. Really, all I'm concerned with is the numerator when it comes to the x-intercepts, x minus 3. Okay, it doesn't even really matter what's down here. And I know I see that what will make each one of these parentheses 0 is negative 4 and x equals positive 3, which means this is our first graph that has 2 x-intercepts, one at negative 4, 0, and one at 3, 0. And then finally we have to find the y-intercept, and to find that y-intercept, I'm going to plug in 0 for x. So there's 4 x's in this problem. I got x plus 4 times x minus 3, except we know x is 0, over x plus 2 and x minus 2. If I multiply that out, I get negative 12 over negative 4, which gives me 3. So 0, 3 is my y-intercept. So a ton of stuff going on here. I have a horizontal asymptote. I've got 2 vertical asymptotes. Highlight this whole thing. And then I have 2 x-intercepts and 1 y-intercept. So now we're going to sketch the graph. I'll be honest, you could plug this function into your graphing calculator right away and get an idea of what the graph looks like, and we are actually going to do that. But I need to see like these characteristics. I need to see the work for them, and I also need to see these plotted on the graph. So what I'm going to do is I'm going to first put dashed lines on my graph here at my asymptotes. So I have a horizontal asymptote at positive 1. Then I have a vertical asymptote at positive 2 and negative 2. So I'm going to go ahead and just put a vertical asymptote at positive 2 and one at negative 2. Then I'm going to go ahead and plot the points that I found. So negative 4, 0, negative 4, 0. Then I have 3, 0. My y-intercept was 0, 3. My y-intercept is 0, 3, 1, 2, 3. Okay. And that technically is enough to sketch the graph, believe it or not. Um, if you're looking at that and you're like, what are you talking about? That makes no sense. We are going to go ahead and sketch this. I'm going to plug the actual function into the graphing calculator just to show you what this looks like. When you are typing this in, you do need to put both the numerator and denominator in its own set of parentheses. Whoops. So I'm going to do x squared plus x minus 12, close the parentheses, and then we're going to divide by the denominator, which was x squared minus 4. I'm going to zoom standard. Okay, and I see that that's what the graph looks like. You can't see the vertical asymptotes, but you can kind of envision where they're at. And that's why I do want you to have this sketched on. You can see right there's 3, 0, 1 x-intercept. There's -4, 0, another x-intercept. And so what I'm going to do is I'm going to go ahead and just sketch this on there. The fact that I have these asymptotes, remember, I can't be crossing the horizontal asymptote. I have to be approaching it. So this is essentially something like this. I should do this in a different color. Let's do pink. So I've got a graph that comes up and levels out like that. The other side was the same sort of thing, ran up the vertical asymptote and leveled out like that. And then in the middle here, it kind of like, since these are both vertical asymptotes, it does have to go or ride along those asymptotes. So again, you are going to use your graphing calculator, but all this work that went into it, I do need to see included in your graphs. So there's our sketch. It's actually pretty close to what the calculator is showing us. But again, we have more detailed information. We have the asymptotes. We have the intercepts. So we have all that good stuff. Okay, ton of information. We're going to do, two more? Yeah, we'll do 2 more with all this, and then we'll go, we'll shut her down, call her good. So if I start with horizontal asymptotes, I've got x over x squared. I see that the larger power is on the bottom, which means that I'm going to have a horizontal asymptote at 0, at y equals 0. Next step is I'm going to factor this thing. So the top doesn't factor because it's just x plus 3. For the bottom, I need factors of 5 that add to -6. So it's going to be x minus 5 and x minus 1. My domain here then is going to be x cannot be 5 or 1. Okay. Those also, neither one of those are removable because I don't have an x minus 5 or an x minus 1 to cancel with the numerator. So those are both going to be vertical asymptotes at x equals 5, a vertical asymptote at x equals 1. And then lastly, I need to do the intercepts. So for the x-intercept, again, at this point, like, we've done the x-intercept enough to know that I'm going to just say 0 equals the numerator. And for the x-intercept, you don't need to worry about for the x-intercept, you do not need to worry about the denominator. So this means that when I plug in -3, I will get 0. So that's my x-intercept. And then for the y-intercept, I'm going to plug in 0 into all the x's. The y-intercept, y equals 0 plus 3 over 0 minus 5 times 0 minus 1, which is 3 over 5. So that means my y-intercept is 0, 3/5. Okay. So again, I'm going to use the 3 asymptotes, and then I'm also going to use these 2 coordinates to give me as much of the sketch as I can without the calculator, and the rest of it I'll just use the calculator to do. So a horizontal asymptote at y equals 0. Vertical asymptotes were at 5 and 1. And 3, 4, 5. And then finally I have -3, 0, and and let's do red. Negative 3 comma 0 and 0 comma 3/5. Oh boy, that's weird. Messed something up. 0 comma 3/5. Oh, it's y-intercept, so 0 comma 3/5. Right about there. Okay. So what we're going to do now is just go to the calculator and plug in the original function. You can actually plug in the factored form, but there's less. It's actually a lot easier to type in the very original without factoring it. So I get x plus 3 divided by x squared minus 6x plus 5. Close that up, graph that. Okay, so I can kind of see we had the formulation. Now, here's this is kind of a weird graph. So this is a vertical asymptote. So what we saw is what the calculator made very obvious is that it's something like this. And what's tough to see, and you would never be able to tell this without doing these calculations yourself, is that this graph is actually going to come down, cross through the x-axis, and then reapproach the horizontal asymptote. And that would require Desmos to know that it goes through. But the fact that I have a x-intercept, and so that means the graph has to cross through that point. But then I also have the horizontal asymptote there. It's kind of a weird looking graph. Does something like that. The rest of it, I'm just going to rely on the calculator to show me. So I got this parabola looking thing in the middle, and then this branch coming up or coming down from the top. So that's all we're going to do for this is sketch something that looks like that. And then finally it comes up from the bottom. Okay. You will notice that because I didn't have any coordinates in this part of the graph, that means I shouldn't have any x or y intercepts. Okay. So simply said, you shouldn't draw something that looks like this because that has 2 x-intercepts. And if that were the case, I would have seen that in our calculations of the x-intercepts. So there's our sketch for that one. If you want to give this one a shot, go ahead. I think this is the warm-up problem. Let's go back and look. Which will make everything a lot easier. Yep. Okay. So all of this information is actually from this warm-up problem is the third one that we're going to take a look at. So I'm going to kind of copy some of this stuff over, or I'm just at least going to copy the factored form. I don't know how to do this. Whoa. Okay. X plus 4 times 2x minus 3. Okay. So I'm going to, first of all, horizontal asymptote, that we didn't do. 2x squared over x squared would simplify to just 2. So that is my horizontal asymptote. So that means the graph's going to be approaching a height of 2 at the sides there. If I factor, this was x plus 4 times 2x minus 3. And on the bottom was x plus 4 times x minus 2. Okay, so we had that crossed out, which means I have a hole at -4, a vertical asymptote at x equals 2. The one thing that we are going to add on here is I would like to know, since I'm graphing this now, not only do I know that there's a hole at -4, but I would like a coordinate for this. So what I'm going to do is I'm going to write this function I'm going to write the simplified version of the function after I take out the x plus 4. And what I'm actually going to do now is I'm going to take -4 and plug it in for the x's here. And what that's going to do is that's going to give me my the actual coordinates of the hole in the graph, so I can be a little bit more precise with what my graph looks like. So this is -11 over -6, which is just the negatives can cancel out, which is like 1.8, I don't know, 1.84, something like that. So I'm going to have a hole in the graph at approximately -4, 1.84. And then our x and y intercepts, again, I'm going to just use that from the top. We found the x-intercept was 1.5, and so is the y-intercept. So we actually have already seen this graph. Again, now we're just kind of like putting it all together. So the x-intercept is 1.5, 0, and the y-intercept is 0, 1.5. Okay. So 1.5, 0. Right there, 0, 1.5 is right there. -4, 1.84 is the hole in the graph. 1, 2, 3, 4. I'm going to make a pretty obnoxious open circle right there, just to know that the graph's going to go through. Then I have a vertical asymptote at x equals 2. Vertical asymptote at x equals 2. And a horizontal asymptote also at 2. Okay. And based on those 3 points, I can kind of guess that the left half of this graph is going to kind of come here. It's going to have the hole, and then it's going to go straight down. And then the right half, I don't know what's going on, because there's two possibilities. It could come up like this, or it could come like that. And I'm pretty sure if we type this into the calculator, again, I can type in the simplified version, or I can just type in the original. 2x squared 2x squared plus 5x minus 12 over x squared plus 2x minus 8, x squared plus 2x minus 8. Now, I did not put that in parentheses, which is going to be a problem. I'm going to go back and insert parentheses there. All right, now if I hit graph, okay, so it does come up or come down from the top after that asymptote. What is kind of interesting is if I type in, if I hit trace, what trace allows you to do is to like kind of follow the cursor along here. But I can also type in -4 and see that it doesn't return a y coordinate. And that's what the calculator will do to show you that there is some sort of discontinuity. So in this case, when I type in -4, I don't get a y coordinate, even though it looks like I've got something right there. Or if I type in +2, which is our asymptote, then I see it also as blank. Any other number I could type in, and it'll give me a value back, such as 12. So all that fun stuff. This there concludes 832. We got one more day just to practice some of this stuff, but good luck.